Oh, and you can also see here that Haskell classes are curried too. Remember, monad state had two parameters, the type of the state and the type of the monad. Here it's being used with just one parameter, the type of the state, and that's equivalent to a one-parameter class, which is a good thing because one-parameter classes are the only things that you can put here in this deriving clause. Okay, and then finally, as I introduce the parser type, I'll also need a function for running the parser, and there it is. But we don't need to look at that in detail. So now I've got a parser monad that has state operations, failure operations, alternative operations, and I can just freely use them together to define the parsing functions that I want. So here, for example, is a function for parsing one token. So remember, the input is a list of tokens, and it's in the state. So let me just get the input. It's a list of tokens. Let me inspect them. Oh, what if there is no token in the input? Well, then parsing should fail, right? So I can just use M0 to represent that. What if I find a token and the rest of the input, tox prime? Well, then I need to consume the token by updating the input, and then I can just return the token that I parsed. Down here is another derived operation that is very nice, that accepts a token satisfying a predicate. So I can just parse my token, use the guard operation that we saw earlier to fail unless the token satisfies P, and return P. So now that all the operations that I've got for free make it very easy to start building my parsing library. Here's a couple of other nice operations. ManyP is designed to parse something that the parser P will accept 0 or more times. SumP accepts it 1 or more times. So I can just say that to accept P 0 or more times, do a SumP, or accept it 0 times. That is, just return the empty list. And SumP can be defined just to parse a P and then many P and combine them using using cons. So I can use the lift M2 function for doing that. And now here is my first actual parser. This parses a positive integer by saying, let's parse one or more characters that satisfy the isDigit predicate. So one or more digits. And then I'll return not the list of digits, but I'll return the integer that those represent. And read is a Haskell library function that can convert a list of digits to a number. And I just want to point out here as well that for doing this part of the programming, Haskell's lazy evaluation is really critical. Why? Well, assume that we were not using a lazy language and look at the definitions of many and some. Many calls some calls many. So that would immediately be an infinite loop. But in Haskell, the cons operator is lazy, in particular in its second argument, and lift M2 preserves that laziness, which means that SumP can deliver results without actually evaluating that recursive call of many P. And so in Haskell, this is a perfectly terminating program, or at least if it usually terminates, shall we say. But it would be an infinite loop without laziness. Okay, and now here is a slightly larger parser. This parses a simple kind of arithmetic expressions. And what does it say? Well, it says to parse an expression, either parse a term A, then parse exactly a plus token, then parse a term B, and then return the actual sum. So this parser both parses and evaluates an expression. Otherwise, if you can't do that, just parse a term. Term does the same stuff, except that it looks for multiplication operators and multiplies the values. And factor is the innermost thing, innermost non-terminal. It parses a number, or if that doesn't work, it looks for an open bracket, an expression, and a closed bracket, and just returns the value in the expression. And I've used this exactly combinator, which just looks for a token that satisfies that it's equal to t. So it looks for precisely one token. So I've written very little code, and now I can write a parser that corresponds very closely to the grammar for expressions that I'm parsing. So it's a nice and classic example. If we try it out and parse the string 1 plus 2 times 3, for example, then this is what we get. OK, you might think that that string should evaluate to 7. Well, it does. There we are. It can return 7, leaving no input unparsed. So what are these other results doing there? Well, if parsing only accepts 1 plus 2, then it can return 3, leaving that part of the string unparsed. And parsing can also stop just after parsing the 1 and leave that part of the string unparsed. So what we're seeing here is that our parser is backtracking, and it's producing multiple possible parse results, not all of which consume the whole input. Do we like that? Would we like perhaps just to get the first one back? All we have to do is change the list type in my monad to a maybe type, and now suddenly we just get the first parse back again. So sometimes you want backtracking parsers. It depends on your grammar. Sometimes you need to backtrack, sometimes you don't. For this simple grammar, you don't. And so I might just as well have used the maybe type as the underlying monad, and that would have been maybe a little simpler to use, maybe a little more efficient. So what I have now is a very nice domain-specific language, in effect, for programming backtracking parsers. I can easily represent alternation, repetition, actions that the parser should perform. So if I'm given a grammar I want to parse now, it's going to be very easy to build a parser for it. And I had to do very little work that was not a part of a monad transformer library. So all of those monad transformers I showed you, those are library code. And the part that I have to write that's specific to parsing is very short. And that's the goal of programming with monad transformers, to get as much work as possible done by the monad transformer library. OK. So I want to show you one more exercise today. List is a backtracking monad, we've said. I've shown you how to add state to list, but there state was a monad transformer, but my backtracking was done by a monad. What if I want to add backtracking to something else? Can I define a backtracking monad transformer? Turns out, yes, I can. So the maybe transformer almost does it, what I want. Here's a reminder of that type. A maybe t computation uses m to compute a maybe a, which means that it can fail by producing nothing, but when it succeeds, it doesn't give me any possibility of generating more values. So how about this type? Let's suppose I define a type called backT, which is like maybe, but it does an underlying m computation, which may fail, but when it succeeds, gives me not only a value, but another backtracking computation that can be used to compute more a's. That sounds plausible, doesn't it, as a backtracking transformer? So this is very much like a list type. It's a recursive type, see? backT appears recursively. But it's like a list type in which there's an m wrapped around each production of an element. So I do an m computation, and then I may get a nothing representing the empty list, or I may get a pair corresponding to a cons. And when I want the next element, once again, I have a chance to do an m computation. So I'm going to make one more change before developing this. What I have here is m of a maybe, But we've already seen that. It's the same as applying the maybe t transformer to the underlying monad M. So I'll work with the type in this form because it means that directly inside a backtree constructor, I have a monad. And I can use monadic syntax, monadic constructions. OK. So is it a monad transformer? Can I write the instances that I need? So here's the monad trans instance. How can I lift an underlying computation? Well, they'll give me a backtracking computation that doesn't backtrack. So I can just perform the underlying computation, lifting it into that monad that's inside backT, and then just return that paired with an M0. What will bind do? Well, it's rather like the instance that I wrote for list types. X bind F will first of all compute X, which is a backtracking computation. If that succeeds, giving me a value A and a way to backtrack, then I can pass the value to F. But if that fails, I still have an alternative, which is to compute more values using the backtracking computation and pass them to F also. Is it a MonadPlus? Well, again, in a similar way, I can define the MonadPlus operations. So how do I fail? Well, I fail in the representation monad. How do I combine alternatives? I compute the first one, and then I return that value, but I retain the other alternatives in the backtracking operation. And if the first alternative fails, because I can't get a value out of X, then the alternative is simply to return Y. Yes?
M0 equals the TM0. So this, the second M0 is from the monad M?
No, it's from the monad maybe T.
Oh,
M. So yes, that's the problem with overloading. It's great. It lets you use the same name for lots of kinds of different things. But sometimes you need to think a little to figure out what they are. But you can see, because it appears just inside the backT constructor, that it must be of the type expected there, namely T. So, once again, this code is very code of list append. If you think of A comma back as being like A cons back. Okay, so it's saying inspect X. If it's a cons, then cons A onto the rest of X appended to Y. If it's nil, then just return Y. So it's analogous to the code for append. And now a simple test is just to say run a backtracking monad computation on return 1 plus return 2. And I haven't shown you the definition, but here I'm using a run backtracking function that collects a list of all the results and returns them. And sure enough, there's 1 and 2. OK. So now I've got a backtracking monad transformer. What can I do with it? Let's see, I can combine backtracking with any kinds of effects. Let's implement Prolog. I've got time. So how many of you have at least seen, maybe written some small Prolog programs? OK, most, not all. So Prolog is a logic programming language. I have a sample Prolog definition here. In contrast to functional languages, Prolog doesn't define functions, it defines predicates. So this yellow code defines the append predicate, which takes 3 arguments, x's, y's, and z's, and it's true if, when you append the first 2, you get the third. And if you read the code here, you can see that it makes sense. If the first argument is the empty list, then it's true that empty list append y's equals y's. If the first argument is x cons x's, this is Prolog's notation for cons, the vertical bar. So if we're appending x cons x's to y's, then we should get x cons z's, provided that, that's what this means, when we append x's and y's, we get z's. Okay, so it's just the normal append function expressed in a logical form. So what's the point of that? Well, the point is that when you execute Prolog code, it solves predicates for unknowns. So I can certainly use the append predicate in the expected way. I can say, when I append the list 1, 2 to the list 3, 4, what do I get? And I say that by passing a variable here. That's an unknown. And now Prolog will solve this constraint that z should be equal to 1, 2, append 3, 4, and it'll show me the solution. There it is. So that's expected. Here's slightly less expected. Let me introduce two unknowns, x's and y's. So I'll say, OK, Prolog. What solutions are there of x's appended to y's should give me 1, 2, 3? And in this case, Prolog produces 4 solutions. X's might be the empty list, in which case y's must be 1, 2, 3. Or it might be the list containing 1, in which case y's is the list 2, 3. Or x's could be 1, 2, or it could be the entire list 1, 2, 3, and so on. So this is what Prolog does. It backtracks to find different solutions for the unknowns, and it can find multiple solutions to the same query. And you can use it like this, to do reverse execution. Is that cool or what? So if only I had, for example, encryption algorithms in Prolog, then decryption would no longer be any problem for me. If only I had a C compiler in Prolog, I could get the source code of Microsoft Word. It's very, very cool. As you can perhaps guess from those examples, it doesn't always work. But never mind that. In simple cases like this, it works just great. So now I want to implement Prolog in Haskell using my backtracking monad transformer. And I'm going to need to implement Prolog variables, so we better understand them a little better. What is a variable in Prolog? Well, it's a placeholder for a value. It's usually, it's initially unknown, but it can acquire a value as Prolog solves the constraints. It's important to note that a variable is single-valued within one solution. They're not like imperative variables that can take different values at different places in a clause, but neither are they really like functional variables because they can take different values in different solutions of the constraints. In a Prolog implementation, a variable is represented by some kind of set reference cell, and it's initially empty, but it can be filled in with a value as constraints are solved. And once you've filled x in with 3, then from that point on, within that solution, x is entirely equivalent to 3. They can also be filled in with references to another variable. So we may not know what x and y are, but we may discover that they're the same at least. And we represent that by making one of the variables point to the other. So this is also filling in x, but it's filling in x with another unknown. And then when y finally gets filled in with a value, then both x and y represent that value. So how can I represent this in Haskell? Well, I'm going to define a type, logical A, to represent a logical value corresponding to type A. And there's going to be two alternatives. Either I know the value, and it's an A, or I don't. It's an unknown variable containing a logic var. And what's a logic var? Well, it's just a reference cell that may or may not contain something, and if it does contain something, is another logical. So when a cell is filled in, it may contain a value, or it may contain a reference to another variable. Okay, what's its IO ref? You didn't think, just because Haskell is a purely functional language, that it lacked updatable references, did you? Oh, no, of course we have them. But because they have side effects, they're in the I/O monad. It's not me, it's the runtime system. So these are the operations that we can manipulate these updatable references with. They all have I/O types. And so it's going to be the runtime system performing them. We can create a new reference given the contents. That gives me an I/O ref containing an A. We can read a reference, then we get the A. Or we can write to the reference a value of the correct type. And that's an I/O computation that doesn't deliver any interesting result, just the empty tuple. OK, so I'm going to represent logic variables as I/O references. That means I'm going to need the operations in the I/O monad. But I also want to backtrack. So let me use back T of I/O as my monad. Now, quite often I/O is used as the base monad that we add things to. And whenever we do that, then we'd like to be able to perform I/O operations. And so we're going to need to lift I/O operations the correct number of times to use them in whatever monad we've constructed. It's handy to define a class just for doing that. So I/O provides a whole bunch of operations, and we certainly wouldn't want to have to write class instances that explain how to lift all of them. So instead, there's a class monad I/O that just says how to lift any I/O operation into a new monad. And instances of this are defined already for any class, any monad you care about. I just have to write one to explain how to lift I/O operations into the backtracking monad. And it's very simple. I just lift them into the monad M, and then I lift them one more time using the backtracking monad transformer. OK, so here's my Prolog monad. I've called it logic. And logic of A is isomorphic to backtrack I/O of A. And now I can just derive a monad instance, a monad I/O instance, and a MonadPlus instance. So I've already got sequencing in this monad, I/O operations, and backtracking, just like that. Very nice. What I have to do to finish the job is provide operations on the logical variables, because they're at the heart of Prolog. So let's see how to do that. Up there at the top, you see the types again, just to remind you what logical variables are here. I'm going to need to be able to create a new variable with no contents. That's what this variable function will do. So I have to create a new I/O reference, of course, containing nothing. I have to use lift I/O to convert it into the right monad. And then I need to tag it with the var constructor here. And I can use lift M to apply the var constructor to the reference. OK, that's going to be what I use to create variables. They're always empty when they're created. When I use variables, I'm going to have to be careful to follow these variable chains. As a Prolog program runs, variables acquire values. They become instantiated. And since one variable can be instantiated to point to another, and that one can later be instantiated to point to yet another, we can end up with long chains of things. And if there is a chain like this, then we're supposed to treat x as in every way equivalent to 3. If we have a chain that ends in an unfilled variable, then we should treat x as in every way equivalent to y. So in particular, when we find out that x should be 3, we shouldn't put the 3 here. That would be wrong. We should put it here. So following these chains is important, and I'm going to have to program that, of course. So here's the code that does it, and it's not at all surprising. How do I follow a value? Well, I'm already at the end. There we are. How do I follow from a variable? I can use lift I/O to read the reference cell. I can inspect it. If the variable contains nothing, then I'm already at the end of the chain. And var r is the correct result. Otherwise, if I find the variable contains something, then I just take it and recursively follow that further. Very simple. OK, so that was a prerequisite. How do variables get values in Prolog? They get it through a process called unification. Unification is very like pattern matching. So, for example, unifying a list 1, 2, 3 against this pattern x cons x's will give values to x and x's. It'll instantiate x to 1 and x's to the rest of the list, 2, 3. The difference between unification and pattern matching is that in unification we can have variables on both sides. So in pattern matching we have a pattern containing variables that we match against a value that does not. In Prolog, there can be variables in both arguments. And that means that we can end up with two variables that we have to unify, and that's when we make one point at the other, recording the fact that they are supposed to be the same. So let me implement unification. I'm going to want to unify all kinds of different types. So I'll make a class, and a type will be unifiable if I've got a unify function that takes two values of that type and does a logic computation to make them the same. So this is the point of unification. It should make its arguments equal by instantiating logical variables. Or, of course, that might be impossible, in which case it should fail. Here's an instance for a simple type, integers. How do I unify two integers? Well, if they're the same, then unification doesn't have to do anything. If they're not, then instantiating logical variables is not going to help, because there aren't any variables in an integer. So in that case, I can just fail. So this is the right definition for the integer type. We just fail unless a and b are already equal. So that's a trivial example. Here's the interesting case. How do we unify two variables? Okay, so if we're given a and b, and we need to make them the same, first of all, we must follow them. Both a and b could be the beginnings of chains, and we need to follow to the end of the chain, and then that's where we look for values or make instantiations. Once we've followed, we have to inspect them, and if one of them is a variable that contains no value, then we can just instantiate it to point to the other one. And that creates this variable referring to another value. If they're both values already, then we can't make them equal if they're, well, okay, if they're both values already, then we can recursively unify those values. So if they're integer values, this will check that they're equal. If they recursively contain variables, then we may do more unification. You might guess from the gap on the slide that there's a case missing here. Anybody have an idea what that might be? Sorry? Well, if they're both variables, then we just make the first point to the second, right? And that's already covered by the cases I've written. No, I'm not going to do the occurs check, nor does Prolog. Aha. What if they're the same variable? Okay, the same variable would be handled by the code that I wrote before, and it'll make that structure. You really don't want to do that. Because next time you try to follow this chain, you'll obviously end up in an infinite loop. So there's an important special case in unification. When you try to unify a variable with itself, don't do anything. Why is that the right thing to do? Because you don't have to do anything to make those two things equal. They already are. They're the same variable. So that's how we unify variables. Now, the one part I didn't show you was the code for instantiating a variable with a value. How should I do that? I have to write to it. So to give the variable, or the reference r, the value v, I can just write just v to it and lift it into the correct monad. But wait a minute. Is that enough? What happens if we backtrack to this point? So when I put backtracking on top of an underlying monad, then, of course, the I/O effects are not going to be undone because we backtrack. So if we come back to this point and we say, okay, we tried to find a solution in which r contains v, but we failed, then we're going to continue backtracking and searching for other solutions. But unless we do something about it, this variable is still going to contain the value v. And it should not, because that's just failed. So what I have to do is get rid of that value somehow. How can I do that? I can just add a backtracking alternative with MPlus that says, when we backtrack to this point, write to the variable again, but put nothing back into it. And then fail, so continue backtracking. I can't produce an alternative solution. There isn't more than one way to set r to v. But I can see to it that if we do backtrack through this point, we clear that variable as we go. All Prolog implementations do this. Normally they do it using a mechanism that's called the trail. So if you've heard of the trail, it's a data structure whose purpose is to make sure that this clearing is done at the right time. But in my Haskell implementation, all I need to do is add a MPlus that performs the right action. Okay, nearly there. If I want to run that append example that I showed you earlier, I'm going to need some Prolog lists. They're not the same as Haskell lists. Why not? Because they can contain variables at each point. So let me define a Prolog list type, which has a nil and a cons constructor, but in the tail of the cons, we have a logical list A, so there might be a variable there. And I'm going to use list where the type A is also a logical type, but I don't have to say that explicitly in this type definition. Of course, I'm going to need to be able to unify lists, and that's easy. How do I unify Prolog lists? Well, I unify nils by doing nothing. I unify two cons lists by unifying the heads and unifying the tails. And if I'm trying to unify a nil and a cons, I'll just fail. I can't succeed. So now, finally, I can write Prolog in Haskell. Here's my Prolog. Here's my Haskell. You might object that the Haskell is longer. Yes, it is. So Prolog has syntactic sugar that makes the notation more concise for writing Prolog. Not such a surprise, maybe. But these two pieces of code are doing exactly the same thing. They have exactly the same structure. The Prolog version has two clauses that are tried as alternatives. Look, so does the Haskell. The first clause unifies the first argument with the empty list and the second and third arguments with each other. Here's the Haskell, unifying the first argument with the empty list, the second and third with each other. What does the second clause do? Well, it unifies, it creates some new variables. So x, x's, and z's are new variables. They're not arguments to the clause. Here's the Haskell that does that. And I've had to, since I already called the arguments to the Haskell function, x's, y's, and z's, I've had to call these x's prime, that's x's in Prolog, and z's prime, that's z's in Prolog. And then it says unify the first argument with x cons x's. There it is. Unify the third argument with x cons z's. There it is. And then recursively ensure that x's appended to y's is z's. There's the recursive call. So notationally, it's a bit more bulky, but the notation is saying exactly the same thing. And if it wasn't 5 to 5, and if I had done this earlier, then I could now start defining more functions in Haskell to make the notation nicer and to make it look even more like Prolog. But semantically, I've got to my finishing point here. Here's a test. This performs the cool application of append. So we just create two unknowns, x's and y's. We ensure that appending them gives z's, and then we return x's and y's as the results. But what I've thrown in here is some functions to logical and from logical that convert between Haskell lists and Prolog lists. And that's going to make it easier for me to see what the result is. So the proof of the pudding is, of course, running the test as a logic program and seeing if it works. And Bingo! Of course it does. There's the solution. I know the suspense isn't that great when you know that I was doing this earlier, but it's still nice to see that it works. So there we are. That's finished implementing Prolog. What have we seen? We've seen a couple of monad transformers. There are a few more very useful ones. And by putting them together, we can easily construct a wide variety of monads. The point of that really is that it enables us to build domain-specific languages, like my Prolog in Haskell, with many kinds of effects, where most of the work is done by the monad transformer library. And I hope you'll agree that there wasn't that much coding needed to make my Prolog implementation once I had the backtracking monad transformer. This says the talk is over. Click to terminate. Yes.
So if you go back, monad C instance for maybe G.
Monad instance for
Monad C instance for maybe G.
Okay. Is it here somewhere?
I think so here you can totally see that you can lift basically that monad state interface to any monad transformer. So you're only using the lift operation of the monad transformer.
Yeah.
And if you now go back to the MonadPlus instance of the state transformer.
Yes.
That one.
Well, I think what